It says I'm live now, so I'm just kind of sitting here on. I don't know why it says it's okay. Is the stream screwing up? Not sure. Don't even know if there's anybody watching it. Let me look at the stream page. Oh, Spooky's here. Spooky, please. I should invite you. Let me send you a message because this is going to be. I'm trying to figure out a way to send you an invitation to the Hangout because I need somebody to bounce off of, somebody to talk to. This is going to be really boring without that. This is about Boolean algebra, and Boolean algebra is the study of logic as it relates to computers and digital circuits. So it could be used in other fields, but let me see if I can invite you via the Hangout here. Invite. You do show up in my list, so I'll invite you. Oh, you don't have a mic? Well, that's still good. I put it in the Great Debate communities. They have a Hangout specifically to post links to Hangouts, kind of prevent the sniping of the Hangout by others. Level of abstraction there, but it's not there. No one's coming in. 2 people responded to my Hangout post and are like, "Yay! It's a Tron reference." Yes, it is a Tron reference. In the original Tron, Sark says, "Bring in the logic probe," and this really big, ugly, mean-looking thing comes along to destroy a door into the communications tower. Well, that's not what a real logic probe does, but there is such a thing as a logic probe. And then there's the entendre of this actually being a probe into how logic works in a binary system. So I thought it fitting. I wish somebody would come in here. Anyway, I'll go ahead and at least share my screen out here, and hopefully it gets somebody's attention. So what this is, we've all heard of the 3 principles or 3 laws of logic, and you know, there's a whole philosophical debate on whether they're God-given or not, and I'm not here to debate that. It's not my goal. My goal in bringing these up is simply to bring up the difference between a tautology and a contradiction, because that is a binary. Binary just means that there's 2 possibilities. So in binary math, there's 2 possibilities, 0 and 1. In a binary logic system, there's 2 possibilities, a tautology or a contradiction, a true or a false. So knowing these 3 principles can help you in your logical thinking, can help you think logically when it comes to circuits as well. And that's very important going forward, because if you build a circuit that is logically flawed, it's not going to do what you want it to do, obviously. So you need to be able to think logically to debug a digital circuit that is, there's something wrong with it from a fundamental logic principle, not necessarily an electrical perspective. And this can be used in the principles of binary logic and Boolean algebra can be used in debates and in other areas, not just digital circuitry. So going forward, logic is the study of patterns of coherent or consistent speech. is most applications are the search for inconsistencies in stories or reports. This is why they use this in the Bible and history and so on and so forth. It rests on the fact that there are statements that are necessarily true and are therefore cannot be falsified no matter what is or is not the case. So it rains or it doesn't rain. You can't falsify that it's raining because it's raining. Boys are boys. No circle is a rectangle. It's just impossible to find, construct, or even imagine a counterexample in which a tautology would not be true. That's because a tautology is true by definition. And and people, this is kind of what they mean when they say common sense, but it's not necessarily common sense. The negation of a tautology is therefore necessarily false. It cannot be verified, no matter what is or is not the case. Negations of tautologies are contradictions. It's impossible to find or construct or even imagine an example in which a contradiction would be a true statement. It rains does not rain at the same time. A boy is not a boy. That's a controversial one. I'm not sure why they're using that, because there's people that would sit there and argue with that. Circle is a rectangle. That's really a good one. A circle is a rectangle. Now there's cases where something is true by definition, but there's a more specific definition, like a rectangle is not necessarily a square, but a square is by definition necessarily a rectangle. So it goes on to say incoherent speech is when someone's caught in a contradiction. We all know incoherent speech. We've heard it before. Bonnie and G-Man come to mind. There's a couple other examples out there. I'm not here to dig on people, but they just spring to mind as soon as I read that. So here's the principles. You've got the principle of existence, identity, uniqueness, specificity, excluded middle, and non-contradiction. So there really is only three. But the first one is the thing, and the other thing is the properties. So that's where you kind of get into things. So everything is something. And I know it sounds just kind of basically, well, duh, everything is something. But it goes without saying that everything is something. We don't even, to have an example of nothing is a contradiction in and of itself. The statement is a contradiction. I have an example of nothing. You can't have a nothing because nothing is by definition non-existent. So a thing is the thing that it is. It can't be what other than the thing that it is. And that's identity and uniqueness. They go hand in hand. And then you get into the properties of things. Specificity is everything has some property, like squares, or rectangles rather. Let's just go with rectangles. Rectangles have 4 sides. That is a property. A thing has or does not have a particular property. A equals A. That's very good. Done a lot of logic in the past. Good. I wish you had a mic. You could come in. All you need is a mic. You don't have anything like a mic that came with your phone or nothing? Anyway. So a thing does not have a particular property. It has or does not have a particular property. So that's the excluded middle. That gets kind of tricky to understand. Like, especially since not everything is a dichotomy. But this applies specifically to dichotomies, which is where binary logic comes in. Because binary logic, when you try to apply it to non-binary situations where there is a middle that isn't being excluded, it gets tricky, which is why computers And artificial intelligence is such a tricky field. So the excluded middle becomes very important in that kind of stuff. And then no thing has and does not have a particular property. Water is wet. Water cannot be dry because water is water and all water is wet. And I'm not going to go into this too much. This is just kind of a review for anybody who watches this later. And this is what you were going into up there with your A equaling A. For every X, there's a Y such that X equals Y. For every X, it is itself X equals X. For every pair of things, X and Y, not X equals Y. So that's uniqueness. And it just, there's different ways to write this stuff down. And it's not really going to come into digital logic that much. It's just good to keep the stuff in mind when you're trying to debug digital logic, because if you've got a logically incoherent circuit, it's not going to do what you want it to do. So then we get into it, and this is going to be a short little broadcast here, because the rest of this is stupid simple. And everything that I do after this is going to build on this broadcast. So if you watch this later, or if you're watching my later broadcast rather about Boolean algebra and you don't have this foundation, come back and watch this, and I will bring this video up in those broadcasts if I remember to do so. And we get into it. Here are in Boolean logic, we call these gates. Digital logic, we call these gates. And these gates, there's one missing off this chart, and that's the NOT gate. And it takes one input and has one output. And since we're talking about binary logic, there's only two possibilities, 0 and 1. So a NOT gate is going to take a 0, and if it has that 0, it's going to have a 1 as its output. Think of 0 as false, and 1 is true if you want to. Doesn't have to mean that, but it's easiest to think of it that way. And then there is the opposite. If you give it a true, it will give out, or a 1, it will give you a 0. And that's not on here directly, but we'll see examples of not as we progress here. So you've got AND gate. It takes two inputs, A and B. They label them 2 and 3 in this chart. Not sure why, because that's confusing to me. 2 and 3, A and B. Just think of 2 as A and B as 3. So if you put 2 zeros or 2 falses, you're going to get a false out of your 1. I don't know why why this is 1, I don't know. It's F. But your output is going to be false. So false and false is false. False and true is still false, because both these inputs to this gate, this is called a gate, have to be true for the output to become true. That's why it's called an AND gate. This and this is true. And then if you reverse that, if your A is true but not your B, you're still going to get a false. Only when they're both true do you get a true. Makes sense so far. Most people do not have a problem with these gates. Or is just, it's kind of like exactly like the AND, except it's what it sounds like. It's OR. So if any of these inputs is true, the output becomes true. So you get 0 and 0, you get 0. You get 0 and 1, you get 1. You get 1 and 0, you get 1. You get 1 and 1, you get 1. So it's literally like either or. Exclusive OR is one or the other, but not both. Okay? Exclusive OR a lot of people wonder what we use this for. And if you hear the term half adder, you might understand it a little bit better. Because when you add Boolean, when you add two numbers in binary, if you add two zeros, you're going to get a 0. If you add 0 and 1, you're going to get a 1. If you add 1 and 0, you're going to get a 1. But if you add 1 and 1, that's 2. 2 is represented by 1, 0. Or it looks like a 10 in decimal, but it's actually 2 in binary. So this is called a half adder because it recognizes that both cannot be on and get true out of its output, F. And it's called a half adder because the carry is lost. There's no carry out of this XOR gate, so therefore it's a half adder. So then on the right-hand column, you've got the N of those gates, the NOT of those gates. And the NOT symbol is literally that little tiny bubble. That's the only difference in the symbol. And a NOT gate by itself is going to have that pretty much with, if you have any electronics engineering before this, it's the amplifier symbol with a single input. So it's a right pointing equilateral triangle, basically. And let me see if I can find one, because I'm sure I can. Update images. Here you go. Plenty of them. I should have had it up here. Let me pull it in here. That's a NOT gate. Okay. So there you go. That's the missing gate from this picture. But it only has one input and one output, whereas this has the inverted. So just like you would expect, the inversion at the output literally inverts the output of the regular AND. So it's exactly the same as the AND, except you're getting the opposite answer you'd expect. So if they're both on, you get a false answer. If they're otherwise, you get a true. With an OR, love it. There are two sorts of people in the world. 1-0 sorts of people in the world. Those who understand binary and those who don't. Then we've got the NOR, which is exactly like the OR, except the output is inverted. Same with the exclusive OR.
I honestly think you want to sit down.
And there goes my phone with HAL.
And think things over.
So then I wanted to touch on, we said the XOR is a half adder. Well, this is a full adder because it accounts for the carry. So this is a single column adding two numbers, and you get a carry out. Now, it's still called a half adder circuit because your circuit does not have a way to get a carry into it. But if you think about the logic, how would you do that? How would you get a carry into the circuit? Well, if you have a carry, what does that do to your truth table of this? So if it's like a 3-input exclusive OR, except it can't be an exclusive OR, it's got to be an OR. So because it's not exclusive at that point, it's either or. It can be both because your carry, you could have 3, which is 1, 1. In which case, your carry is your overflow, but you still need to be able to show 1 as an output as well. So you'd have this, and your S would output to another OR gate, and then your carry in would be that OR gate. Pretty simple stuff. So the reason I'm keeping it this simple, just going over what gates there are, is because there is math that goes along with this, because the symbols, the logic symbols, let me see if I can pull up the logic symbols. I had a hard time finding these before. I was trying to get a program that would give exercises because Steve's been doing these math ones where he's got the math program, but it won't show the right symbols for what we need for digital electronics. Because when we get into what's called Karnaugh maps later, it's very important for products of sums and sums of products that we understand that these symbols directly relate to these gates. So logic operators, maybe. Because they don't really do this real well. Oh, come on. But anyway, your AND is multiplication. If you really look at it, it's multiplication. So the logical operator for AND is the dot. We use that logical operator. And it's a product. Because if you take 0 times 0, you get 0. If you take 0 times 1, you get 0. If you take 1 times 0, you get 0. You take 1 times 1, you get 1. So AND is multiplication, if you look at it a certain way. OR is kind of addition, except your carry in, it kind of messes up with carry. XOR is, so we use the plus sign for OR, but it's for exclusive OR, it's the plus sign with a circle around it. And when we get into Karnaugh mapping, there's two ways to go about Karnaugh mapping, and the ultimate goal of which is to get a product of sums or a sum of products. And it's used for the simplification of circuits, because a lot of these circuits can become very complex. I mean, this may look simple to you now, but when you start talking about how many of these things are in a microprocessor, it gets real complicated real fast. And just to give you an idea of what's inside these things, that right there is some of the circuitry. So that's a transistor, that's a transistor, that's a transistor, and that's a transistor. So there's 4 transistors in this A and B. And there's 4 transistors in the OR. They're just arranged differently. And it's, it's kind of neat to look at this sometimes, but when we design these circuits, we don't really think about, well, for every AND gate or every OR gate, there's 4 transistors. But when it comes to actually producing a microprocessor, they're very aware of how many of these transistors. When you look at the specifications for a microprocessor, they're talking about billions of transistors on a chip at this point. So, and that's why they're so expensive. So anyway, I thank you for watching, Spooky. Hopefully I didn't drone on too much, but that's going to bring it to a close. And I'm trying to keep it simple and keep it short. That way people aren't too bored. Half an hour, 20 minutes to half an hour is kind of where I want to keep these, because it's dry stuff. It really is. Oh, wait, we've got somebody here. Yes. How do I get this person in? How do I get them in here? It won't let me. I don't. Show and broadcast. There we go. Druss, you there?
Howdy doody.
Hey, finally somebody came in. All right. I'm more than happy to keep talking about this stuff if somebody's here. I just don't want to talk to an empty room. It gets kind of
No. It's quite interesting. This is what I did as my second course at uni was electronics engineering.
Well, yeah, I mean, I'm a computer engineering major, so this was very much what I did in. Yeah, I kind of went about it in a different way, but my background is I went to tech school. So tech school is an accelerated 2-year degree in 1 year. So my associate's is computer electronics robotics. So we didn't actually design a microprocessor in that course, but we went over this and we went over assembly, and that assembly included 68,000 in Intel assembly, which obviously builds on all this because this goes into a microprocessor, and machine language, of course, builds on what's inside the microprocessor. So then, of course, you get into computer engineering, which is the other part of this. We actually designed and built a microprocessor, including the microcode and everything that went along with it. So,
yeah, I mean, I use a really good analogy when I'm trying to sort of talk about this kind of stuff to people that don't understand it, and I kind of describe it a bit like a shopping mall.
Yeah.
So if you think that each one of the shops in your mall is like a core in a CPU. And within that shop, they're going to have product and function,
right?
And which are kind of like your transistors within that core,
right?
And then what you have is you then have the infrastructure. The mall's the whole of the the wafer, the chip rather, and then the mall is the rest of the infrastructure. So that's the stuff bringing stuff into the store, making sure it's got the right amount of electricity to run it, making sure that the waste stuff is taken away,
right?
Sort of analogous way of sort of describing how CPU works.
Right.
And then I put that mall in a city, and then the city is the computer.
Right. Exactly. And that's a really good way of looking at it, too, because the microprocessor doesn't really do a whole lot by itself. It needs a lot of supporting stuff for a fully functional general-purpose computer to work. So,
yeah. Or as I say, that they only know two things, yes or no.
Yes or no.
0 or 1.
And everything that they process is a chain of numbers, no matter how you look at it in the real world. Even this giant screen and you and I talking over the network is all a bunch of zeros and ones when you get down to it.
But I think one of the things people don't understand, I think this would be a valuable video in the future, is, and you touched on it, the way we talk to hardware within within the computer is by invoking machine code. Which is kind of like your first layer language, and it's how we used to program computers back when I was young.
Definitely. I definitely want to, when I get to microprocessors and what a microprocessor is, because obviously that's a little bit further down the road. I have to get into latches and registers and so forth, and we're talking about feedback at that point. It's different. I mean, all this stuff builds on it. I mean, you could build everything out of the gate on the left-hand side here. You'll spend a hellacious amount of money on 7400 series logic, and yeah, but you could build anything with it.
But I actually like the fact that if you understand this kind of process, the if, and, or, but,
right,
sort of operators that you're talking about, it's actually a very useful way of looking at how you apply logic in life.
Right.
It's almost like a Socratic method in IT.
Well, and that's why I started out with this introduction to logic. I did actually start out with the principles of existence, identity, uniqueness, specificity, excluded middle, non-contradiction. Because it flows from that. And these build on dichotomies, and the only thing that kind of gets you is the excluded middle, because life is not necessarily a dichotomy.
No.
But binary logic is definitely a dichotomy.
Actually, just on a total sort of segue comment, have you been reading what the Japanese are trying to do with quantum chips? So they've got a design plan together for a quantum chip to basically.
I've heard
It's
a little
basically
bit about
using token ring effectively.
it. Okay.
I don't know if you know token ring. It's a networking standard back in the
Yeah,
the
it's sort of
80s.
didn't catch on like Ethernet, but yeah.
Oh no, it was actually it was much more popular than people gave it credit for, because you had two choices back in the day, which was BNC, which was a pain in the ass because basically everything had to be connected.
Or it was broken. Yeah. If
Yeah.
it wasn't connected, it was all broken.
Yeah, and you needed a 50 ohm terminator on the end of the cable to bounce the signal back.
Remember that, because the first network we got in our school back in high school was a BNC RG58 network.
So token ring obviously it was kind of like the predecessor to structured Ethernet, Cat3.
Right.
But the cool thing about it was it had this concept of having a token that was passed around.
Right.
All the machines on the ring. So when you had, it was like having the speaking stick.
Right. It
it eliminated was broadcast storms.
Right. And that was a very cool thing to eliminate back then, because broadcast traffic brings those slower networks to a complete crawl, and it'll still bring a network to a crawl today.
I actually fixed a problem last week with a customer. I was actually having a call about a security issue, and the guy was moaning about his network and this, that, and t'other were happening. And I said, just a silly question. You're not using two different brands of switches between your core and your floor. And you don't have auto-negotiate set on one and fixed on the other. And he went tappity tappity tap. He said, yeah. And I said, I think that's your problem. That's what's causing your networking to screw up, because it's going to renegotiate. The auto-negotiation is going to try and renegotiate every time.
Right.
And it's going to be spitting out, because it's Cisco, it's spitting out CDP packets.
Right.
That's not very cool, because the other switch goes, huh?
Right. The other switch doesn't know what Cisco's saying to it. Because Cisco's got to be different. I'm not saying Cisco's bad, but they've got to be different. They can't just do what everybody else is doing in the world.
Well, there was always the bar. Every manufacturer. I mean, I used to do, admittedly my networking's a bit out of date. It's probably sort of 10, 15 years out of date now. But everybody used to chew into the SNMP MIB.
Mm-hmm.
You had the proprietary side, which were manufacturers supposed to use, and then you had the standard side. Oh, RFC 1514, I think.
Yeah.
Flashback. And that sort of didn't help, because one of my jobs, and the only reason I know about this, is I used to write SNMP traps for banks, which was possibly the most boring job you can ever do.
But important. Right, because it's a bank. You need to know when stuff's happening, and we need to know now.
I'll tell you my favorite bank story is I went in to do some comms work, and this was in the US. And basically, I stuck on a discovery tool, and we discovered all the network, and it tells me what all the links are, and it tells me how much traffic's going over them and what speed they're set to. It really trawled through the MIB, and also went into the proprietary portions of certain MIBs as well. It was quite a cool little tool. But one of the things that we found was they still had, I think it was 5 offices that were still live. Even though they'd sold the buildings. And what they hadn't done is shut off the frame relay. And the worst thing was they still had traffic going over one of those connections.
Oh, dear.
Yes. And I was being told emphatically, no, we don't have those offices. And I said, well, you may not have them, but
somebody's sending traffic.
Stuff's going on.
Right.
All I can look is the data. Yeah. All I can look at is the data. It starts here, it ends there.
Right.
I can see where that IP address, which city it's based in.
This is getting way ahead in this series of videos. We're talking about the management information base and simple network management protocol, and this is used to monitor networks, for those who don't know out there. And a trap is something you can set on a remote end to send you an alert, basically. And correct me if I'm wrong on how this is done, but it's something your management station receives from the other end, right?
Well, what it is, most devices, whether it's, there's an SNMP MIB in most server OSs, there's an SNMP MIB in a lot of desktop OSs, printers, switches, they're sticking it into a lot of IoT devices, a simplified version of it. And effectively all it is it's just grabbing a whole load of data or keeping a whole load of settings.
Right.
And I'm now interested to see if I got that MIB specification right.
So it goes out there and it tries to, you've got a management station, you've got an agent running on a remote machine, and that management station goes out and queries, and the MIB takes that number, because it's querying like everything else in computers. It's just querying a number, but that number in the MIB is what that number means. Like, for instance, it's this particular number, for instance, means location.
What I can also do is I can set up conditions,
right,
to then create alerts off the back of that. Again, if we go back, your logic sort of page on there, so I can say that I expect to see X. If I see Y, do this.
Right, and that's what a trap is.
Yeah, and a trap is basically where I go in and I sort of go folder 1579834, which is just like going through a set of folders on your desktop and just counting which folder you're going to. It's not quite the same, but that's enough analogy. And then that's how I'd specify where the location of my value is.
And there's standard MIBs, and then there's manufacturer specific MIBs, because each manufacturer has their own space in the MIB table that they can define what each thing means.
Yeah, so it's very similar to if you've got an IP address, you can associate a port to an IP address. Right. Some of those ports have specific functions attributed to them. Some are just ports you can use. So I won't go into that because that's getting overtly complicated. But what I wanted to say, because I was going to keep this short, so I've got to go and chuck my kids to bed, is, if you're ever doing Hangouts like this and you want a techie nerd, then I'm pretty okay on some of this stuff. I didn't go down into the depths of the sort of processor logic, but how actually stuff works in a real environment. And I understand the 7-layer protocol decode, or the OSI chart.
Right.
I understand that pretty well, and also I understand when it was more than just TCP/IP, which is all we see nowadays. Right. So I worked on Banyan Vines. I worked on OSI.
I worked on the Vines in a long time. Let's talk about your esoteric networking protocol.
Well, I'm an old person, so that's why.
Well, I mean, you and I were talking about Ethernet when it was on coax, so that's in 50 ohm terminators and things like that. Yes. And how awful BNC connectors are.
Yeah. This is what technical people do. We do a few lines that says, he has an idea of what he's talking about, and I go, so does he. And we'll put little things up, and it's like little sort of, it's almost like a secret Masonic handshake between techies.
Right. Like if I start talking about DNS, I'm sure Druss would probably know what DNS is all about.
Yep.
But the specifics of how to set up bind the DNS server might be not in his purview at this point. It might be outside.
Yeah.
Or not.
I quite like DNS. It's most of what I do nowadays is more security based.
Well, I mean, I've been a system administrator since I want to say '98. That's when I first started working in system administration. And back then, dial-up was the thing for consumer. And I worked for ISPs, and I worked for telecom, and I've worked for Oracle, and I now work for a place called Infor. So
I know Infor, yeah, database.
Well, it's database, but they do other stuff, just kind of like Oracle does other stuff too. And but if I work for their enterprise asset management team.
Oh, I know all about asset management.
Oh, well, I don't.
Right,
I know
okay.
that I know how to do cloud-based management of a product. I don't really know the product that well. So
it's more. I mean, depending on what type of asset management they're doing, it's more about, you know, going back to my example with, you know, scraping the data off that bank. It's about going out discovering stuff.
Right. I mean,
because-
I understand intellectually what enterprise asset management is all about, but I'm not the designer of the software. Let's put it that way. I'm just the manager of the cloud service that we provide for customers.
I was going to say, if you want to sound really cool, asset management involves 5 questions and a 6th answer. Yeah,
5 questions.
This is something this is something I used to work for a company out in the US many years ago. And this was one of the things that I came up in a brainstorming sort of session with some much smarter people, because we were trying to simplify down quite a complex sort of concept, and this was just after Y2K, and people suddenly realized how little they knew about what they owned, unless you were French and you get taxed on it.
Right.
And it basically, you know, it all comes down to, you know, these 5 questions. What have you got? Where is it? Who's using it? How's it performing? Is it doing what the business needs?
And that makes sense.
That gives you your output, which is how much is it costing you?
Right. And if it's a negative cost, that's a good thing, because that means it's making you money.
Well, that's where you start to then look at functionality and value.
Right.
So value can incur cost because it gives a greater benefit, but negative value is bad because it actually gives a lesser benefit when compared to the cost. And this is where people start talking about return on investment models and all that kind of shit.
Well,
anyway, I should dash. I did want to drop in and say hi just because of the subject matter you're on.
Well, I appreciate it. I was hoping more people would show up because, I mean, you said you love the Tron reference. And yes, that is very much a reference to Sark in the original Tron. And I explained, yes, there is such a thing as a logic probe, which is nothing like the logic probe they used in the movie.
I'm looking at the DVD sitting up on my shelf. I actually played that movie for my eldest kid, who's just 13 now, a couple of years ago, and he was just blown away with it.
Well, I mean,
you know,
the concepts it exudes are kind of interesting, but it's fancy, it's fantasy, but you know, it's interesting.
And it was almost kind of, in an obscurely stupid way, in certain very specific areas, kind of interestingly with the language they used.
Right.
They really did. They did try and use good language, but I think for me the thing that impresses me most is actually how it stood the test of time.
Right. Well, you got the sequel, which is about his son, and that was well done. But again, it's fancy, and it's kind of like, I don't know. I liked it it's a good movie, but it's not a real representation of what we're talking about at all. So
yeah. Excellent. Anyway, I shall let you go, and thank you very much. And for anyone that's listening, thank you for listening.
Thank you for listening.